So the lecture of today is just an introduction to the problem and to the question that is related to new concepts in damping, generation and control. We will look at some new theoretical formulation for the problem, and at the same time we are interested in some industrial applications that we will discuss together in the final part of the presentation, not of the presentation of today, but in next presentation. So the new concepts related to damping, generation and control are problems that are gaining interest on both sides, physics and engineering. So on the side of engineering, we have a lot of devices and a lot of technical problems that can say gain some particular performances when the concepts related to the deep root of damping mechanism and say dissipation mechanism are investigated, following a different point of view with respect to the point that is frequently used in engineering. Just to give you an idea of what are the subjects that we are going to investigate, so I would like to spend some words about a short introduction related to the Hamiltonian damped systems and the concept of hidden variables in the analysis of mechanical system. So, and then a few words about the context in which we are interested in developing such a kind of analysis, and in particular the field of complex and uncertain systems, and with particular emphasis, of course, of engineering, and some mention to the field of physics that are interested in this kind of formulation. So we want to point out a variational statement of the problem in order to understand which is the mathematical frame of the problem we are investigating. Then, starting from tomorrow, we will show the equation, the so-called equation for the master. So I would like to say that the main part of the arguments that I will present are part of research project that we are developing at the University of Rome. So the equation for the master and the band limiter process are two main points that are part of the original work that we are doing in this field. Then there is a third point, that is a variational theorem for the minimization of damping, for maximization of damping. That is also an original result that I would like to discuss with you. And as a last point, we can present some results related to industrial application to the university satellites in the University of Rome, and more application that can be dealt with this particular approach. And of course, at the end, some conclusions. So what is the main point that we would like to analyze here? So we know that Hamiltonian systems preserve their energy. That means that they work with a constant total energy. On the other side, damping is an effect that tends to reduce the amplitude of oscillations in a mechanical system, say that we can use this definition. So our interest is in Hamiltonian systems exhibiting damping. Just looking at this, this definition, intuition would suggest, in some sense, an apparent contradiction between the energy preservation concept and damping concept. But really, the main point of our investigation is just to connect these two concepts, and from the comparison, the systematic comparison between the energy preservation process and damping process, we can gain a new point of view about dissipation. So I would like to show you a video in order to understand better what is the problem that we are considering. So this is an experiment that is performed just using something that can be considered a very simple model, in which we have a very simple oscillator in which there is a gas dynamic bearing in order to decrease as much as possible the inherent dissipation of this oscillator. As you can see from this movie, actually the dissipation is very low. And so this is just for comparison with the next video that I would like to present to you. So this is just a principal oscillator in which we have just a mass spring system. Now we want to show that if we consider a more complicated system in which we have the same principal oscillator to which we attach a cluster of secondary resonators, you can observe for this system a quite intriguing effect. But without further comments, I would like to show you that the energy that was initially contained into the primary oscillator is transferred to the set of secondary resonators, and the secondary resonator themselves are not really very highly damped. So this is just something to explain a quite intriguing characteristics of the system that we are going to investigate.
So you want to make us believe this happens by chance?
No, this exactly the contrary. It doesn't happen by chance, but it happened because there is an intrinsic dynamics that deserves to be investigated behind this kind of phenomena. So intuition would suggest an apparent contradiction between Hamiltonian and damped systems, but say that the experiment that we were watching before is a good illustration of the following points. Damping is not necessarily related to dissipation. So what happens to our primary oscillator is apparently a sort of damping, definitely. So the amplitude of the motion decreases as time increases. But it is obvious from the video that this damping phenomena is not necessarily in this case related to dissipation, but just is related to the fact that energy that was initially concentrated into a particular coordinate of the system is just transferred in another part of the system. So this is the first remark. The second remark is that the system with several degrees of freedom can show dissipation-independent damping, the master, the principal oscillator that we were showing before, in the motion of one of its coordinates, and it means we can, especially when we observe just one part of a system, even if the whole system is conservative, we can observe locally phenomena of damping, so of energy decreasing, because energy is just moving apart from the observation site. Thus, this contradiction is only apparent. As a general consideration, we can say that the physical matter consists, as we know, of atomic lattices that can be modelized as a Hamiltonian system. This is the usual way of modeling atomic process. So atomic lattices exhibit damping as a consequence of their tendency to reversibility. So energy preservation and damping are perfectly compatible notions. And this is very important because now if we look at the problem under the mathematical point of view and the physical point of view, we can completely separate the two concepts. So we can have a conservative system, but we can observe just looking at some part of it, we can actually look at damping phenomena definitely, even if the complete system is conservative. So we can have an energy preservation process as a whole, but at the same time, if we limit our observation to a limited part of the system, we can observe damping. So we can observe actually an energy reduction. So this is the main point of what we are going to discuss. So we call master the part of the systems that we observe. Actually, it is just the part that we want to describe. And hidden variables, or unmonitored part of the system, the part that we can neglect in some sense. I would like to add something and add some consideration about what we mean that this is the unmonitored part of the system. Of course, if we have a system that has a certain number of degrees of freedom, we can select just one of them that we can call the master, and we want to describe in mathematical details just this single coordinate of the system. The rest of the system, of course, has an effect and has a deep effect on the dynamic of the particle or the coordinate that we are observing, but we don't want to describe the detailed equation of motions for that particle, so for the remaining part of the system. This is our aim. So we can define more or less the situation. So suppose that you are dealing with a system that has n plus 1 degrees of freedom. So x1, x2, x3, xn, and there is the master. That is just one of them, but we have the red ball just because we are interested in it. Then we can introduce a different description of the system. So, of course, the complete description of the system is given by vector x that has in its first position x, that is the coordinate for the master. Then we have x1, x2, xn as the coordinate of the remaining part of the system, meaning the hidden variables. So the variables that we don't want to describe in details. Then we have that we can correct the degrees of freedom that we want not to directly describe into this vector, this x flex. So x flex is x1, x2, xn, and contains all the degrees of freedom that we don't want to directly describe. I will talk later about the importance of this approach, both in physics and engineering. So why it is important in physics and engineering to take this particular point of view about the systems that we are investigating, but without any kind of special effort of fantasy. Everybody can understand that there are many situations, for example in physics, in which we are not interested in describing the system as a whole, but just we are interested in describing just a limited part of it. But say that this is the usual situation in which we work. So if we are available to describe the entire system that we are investigating, of course this implies that we are not able to formulate any kind of mathematical model for the reality that we are studying, because generally what we have to do is just to cut a piece of the reality, and then we want to limit our model to this part of the reality that we are investigating. So the remaining part, say the environment in which this system is put, is not interesting for us. But of course the environment can have an effect on the system that we are investigating. So our approach is that we don't want to describe in details the parts of the system, but we want to take into account in the motion of the master the effect of the environment. This is the case also in many problems of mechanical engineering, in which you deal with a very complicated system, but your interest is primarily related to a sub-part of the complete system. And we will see several examples. Well, we have some problems with, this is the version of PowerPoint. Okay, this strange symbol probably means a dot on the variable, so time derivative. Okay, this is a new symbology that we want to introduce. So say that if we look at a Lagrange point of view, an Hamilton point of view of our problem, just in view of what is the final aim, the final goal that we are proposing, it is natural, in some sense, to decompose the Lagrangian function, that is the L on the left-hand side, in three in three contributions. So in general, the left-hand side depends on all the variables that we can introduce in order to describe our system. That is just the vector x dot. X, as you remember, contains all the variables that describe the system, so the master and the hidden part. Then we can split the Lagrangian into three contributions. The first contribution, that is Lx, depends only on the variable related to the master, so x and x dot. Then we have two other contributions that are naturally present in the general expression of the Lagrangian. The second contribution depends both on the variable of the master and on the hidden variable, and the third contribution depends only on the hidden variable. So we use these three contributions. And of course, for this system is valid the Hamilton principle, the minimum Hamilton principle. So the Lagrange equation for the system can be written in this form, the usual form. And actually, what we want to do is to decompose the Lagrange into the three contributions, explicitly writing down the equation for the master, that is just the first Lagrange equation of the set that you have on the screen. And then we can couple this equation with the set of equations related to the hidden variables. It's quite an obvious procedure. So in the equation that you have on the screen, the first just described, as you see, involves only derivatives with respect to x dots, meaning that it is the equation for the master. While the second set of equations are the equations related to x flex, that are the variable of the hidden part, the unmonitored part of the system, so the part that we don't want to describe. Actually, of course, in this formulation, we are describing everything. So suppose, just for clarity in the following, that x star, x flex star, are the solutions of these equations. Okay? Suppose these are differential equations, and x star, x flex star are the solution of this system of equation. So what is our goal? So our goal is that we don't want to use the second set of equations. So we want to erase the second set. Sometimes it is a very good point, especially when you are dealing with systems that have an extraordinarily large number of degrees of freedom. So there are problems in engineering, so in modeling, for example, aircrafts, in modeling cars, in modeling ships, in which you are compelled to use more than 1 million of degrees of freedom in order to describe properly the dynamics of your system. But generally, maybe that you are not interested in the knowledge of the displacement or vibrations or of any part of the car body, of the fuselage, or the hull ship. So you are just interested in particular analysis of some parts, some pieces of the very complicated system that you are analyzing. So it is important that we have a chance of just selecting few degrees of freedom that are the ones that we are interested in, and then we can chop the part that, of course, it is important in the sense that the interaction, the effect on the monitored variable is important, but that we don't want to describe in these mathematical details. So we want to erase the second set, and then it could mean millions of degrees of freedom that we are simplifying. But of course, in this equation, we have a problem that of course, if we just preserve the first equation, we cannot solve the first equation without knowing something about the part that we are erasing. Because, of course, there is a part of this Lagrangian function that depends on the hidden variables, of course. They are coupled equations. So what is the challenge here? The challenge is to understand if and under which conditions it is possible to replace this very complicated term that actually takes into account the interaction between the particle that we are observing and the environment, just leaving its expression depending only on the variable that represent the system that we are investigating. We can anticipate that this kind of replacement, that is a replacement of a complicated expression in terms of x flex, is not generally possible. But under some conditions that can be met in practice and can be met in the analysis of very important system, this replacement is allowed. This means that we introduce or a negligible error, or we can introduce at least a limited error that we can evaluate. Okay? So it is quite an intriguing point of view. What is the characteristic of this replacement? Well, if you, I would like to remind you the videos that we were watching before. So one of the characteristics is that if you have isolated under certain conditions, because it is not a general system, but we will discuss later about that, we have a single particle, a resonator, and then you have a cluster of other degrees of freedom. Well, what is happening in that case is that the energy that is initially conferred to the principal oscillator is suddenly transferred to the cluster of oscillator. So, in some cases, that are cases that we want to investigate, this kind of effect amounts globally to a sort of damping effect related to the particle, to the sub-part of the system that we are observing. Okay? So when this process is a process of energy release from the part that we are observing to the remaining part of the system, we probably have the chance to describe this kind of contribution in terms of a sort of equivalent dissipation. Please.
But you have also seen that the remaining part gave back energy
Yes.
to the main part.
Yeah.
So this Q may be different from dissipation.
Oh yeah, it is. In fact, in the next part of our presentation, we will follow two main points. The first point is to provide a general expression for the part that we are, that is the candidate to be replaced by Q. But before doing this, we have to understand the nature of what we are erasing there. So the first step is just to understand what is the mathematical nature of the term that is in the blue ellipse. The second point is to see if there exists a corresponding expression that can be expressed only in terms of x dot, x dot, in order to make this replacement and to check if the error that we are introducing in this way is important or not. So, in some cases, it happens, because of the nature of the part that we are erasing, that there is a sort of reactive process. So you transfer the energy from the particle that you are observing to the remaining part of the system. After a certain time, the energy is reorganized in order to be transferred back to the single particle that you are observing. In this case, I would like to anticipate to you that, in fact, we don't introduce a damping necessarily. So in the first step, we introduce something that is much more complicated, in some sense, that is a convolution integral that relates the x displacement to the force that is represented by the interaction with the environment. So actually the term that we are introducing there, the Q term, is a convolution term. in which the kernel of this convolution depends indeed on the particular dynamics of the neglected part of the system. And in this case, you can have this process that you are describing. So the energy comes back to the master. One of the points that we will discuss later is just the investigation of the class of the systems that do not present this kind of process that you are describing. So for which the energy is definitely transferred to the master, and then you cannot obtain a sort of reflection of the energy from the unmonitored part to the master. So exactly what we want to do is this replacement in equation of motion. But of course, the main point is that if X star is the solution of the complete problem, so studying the whole system, well, we ask that X star would be the solution of this reduced equation, of course. So we can replace the complicated term by Q, but of course we want that the dynamic of the system is at least similar if it is not equal to the original system. Otherwise this replacement is meaningless.
You capital could depend also on initial conditions?
Yes, in general it depends on initial conditions, but as we will see in the following, but in our analysis we are thinking to initial conditions that are 0 for all degrees of freedom, except for an impulse that is originally communicated to the master at the time t0. So aim of the present investigation is just to understand if the replacement of V, that is the complicated term, the interaction term, by Q is possible. Physically, this means the interaction between the master and the unmonitored part of the system, that we can call also the environment, can be described in terms of the master coordinate only. And as I said before, our analysis attacks the two following points. Provide a general model for V. This is very important, of course, because otherwise we cannot understand what we are doing. So the first point is just to understand how the interaction process can be modeled. And the second point is what are the conditions for which a suitable Q can replace V. Just come back to the original question. So our original system, of course, is a Hamiltonian system, meaning that its energy is constant in time, meaning that the Hamilton function, that is the summation of the kinetic plus potential energy, the time derivative is equal to 0. This means that our system is conservative. This is a direct consequence of the Hamilton equation. But for the subpart, so just for the single particle, of course we can introduce the total energy of the single particle as the summation of Tx Ux without this notation. So the energy that is associated to the single coordinate can exhibit a decay in time, even if the system is conservative. So energy time invariance, of course, is a property of the collective motion of the system, but it is not a property of the single coordinates. So this is the very simple explanation why we can observe just if we look at a part of a Hamiltonian system, a dissipation process, a sort of damping process, but we cannot observe, of course, an energy decay looking at the whole. So if I have time, and if you are not too tired, so I can just finish this short introduction. So what is the reason why we are attacking this problem? So what is the motivation? Well, I would like to tell you some experience in real engineering structures and engineering design, and then to suggest also what is the part of physics from which we can take analogies and interaction that is related to the problems that we are discussing here. So the model design process of an engineering system are characterized by an increasing complexity. That means that you demand to your model a high capability of prediction of the system design at a design stage. So where we are designing a special system, and actually we want to develop virtual models. With virtual models means that we don't need to produce prototypes, and then we can model the effects of the environment on the device that we are designing directly by computers. That means by mathematical modeling of the system itself. So if we want to be very capable in this kind of prediction, of course the system must be complex. And the counterpart generally of this modeling improvement is paid in terms of a very large number of degrees of freedom. This is, for example, I would like to give you some example. When we are doing, for example, mathematical models for seats in a car. So you can want to predict what is the vibration level or the noise in a car, but I don't want to produce any kind of prototypes. Then I must be able to produce simulation on the computer in order to understand which is the best combination of physical parameters in order to reduce, for example, the noise inside the car. It is a very important point, because if we avoid to build up any kind of prototype, of course, the costs are much less. And this is, of course, a problem to which industry is very sensitive. So it is important to be able to describe the behavior of a complex system by in a way that you can avoid experiments. So I would like to discuss with you what are the roots of complexity in this kind of system in engineering. So here there is a finite element model of a cruise ship. And this is just obtained forcing the system using some force that comes from the vibration of the engine. So actually, as you see, typically the wavelengths that are involved in the vibration of this very large structure can be very small. So if you have very large structures and you have relatively high frequency vibrations in the structure, you have that the wavelength is very small. This implies, for the Shannon theorem, that if you want to describe properly the dynamics of such a system, you must use definitely a very coarse mesh in your finite element models, since you have to sample your function suitably, and suitably means that you have to use small steps in order to properly describe the motion of your system. This is a problem of complexity, because of course the description of large structure with relatively high frequency excitation generally implies that you use a finite element model with a very high number of degrees of freedom. This is a very big problem, because large dynamics problems, of course, needs a computational effort, a computational burden that is very high. But it's not the only problem. If you have 2 million of degrees of freedom, you have problems of uncertainties into the parameters, and you have frequently Hill conditioning into the analysis of this problem. So even if you accept to pay the computational effort in order to obtain a response from a system that is 3 million degrees of freedom, you have a problem that if you change very slightly some parameters, especially in the high frequency range, there is a very high sensitivity of the eigenvalues of the problem, and then you obtain completely inappropriate response when compared with experiments. So it is a very big problem. Another problem of complexity, these are some structure that we analyzed in our lab. This is the dashboard of a car. The dashboard of a car is a very complicated system, because of course you are interested, for example, in a high frequency vibration of the dashboard, but And so you have to use small elements, but even because the complexity, so the variability of the structural elements that you are introducing there is really unbelievable. And there are a lot of components there that is very difficult to describe in order to find suitable models. So there are cables, there are plates, shells, beams, but there are also other elements that cannot be really assimilated or matched by library elements that you can find. So there's another problem for complexity. This is the case of a seat also. This is in our lab. If you want to produce a mathematical model of a seat of a car, well, it is an extraordinarily difficult problem. In order to modelize, so the structure of this system is so much complicated that if you have to produce a very complicated finite element model, but at the end using 1 million degrees of freedom in order to reduce this to finite element model, then you put this complicated model into the finite element model of your car, you put the seats that you spent 1 year in order to model it, the results are nothing, because the matching with the experimental result is really poor. So there are a lot of problems. This is important to underline the theoretical analysis of very complicated systems. Nevertheless, and although we have very strong computational capability today, it is not sufficient generally to avoid a clear theoretical analysis of what we are doing, because in many cases, even if you have very powerful numerical tools, they are more or less not usable if you have not a clear understanding of what we are doing. So example of system considered complex, so the complexity comes from small scale dynamics, meaning high frequency, so a lot of degrees of freedom. Heterogeneous systems, so presence of many different structural elements, joint complexity, and geometrical complexity, and also from nonlinear phenomena that are generally very present in this kind of system. So many elements produce complexity, however, the effect is generally that we have to use a large number of degrees of freedom. In addition, complex systems needs for their description a large amount of information that is not always available, meaning that since we have to use some parameters in order to complete our mathematical model, we have some uncertainty in the model. So I would like to talk to you about the seat. It is a trivial example. But nobody provides you the characteristic parameters of that kind of plastic that you have there, of that kind of particular material, of that particular joint. So these are unknowns actually in the problem. So we can treat them as stochastic parameters. So you have a quite intricate problem, a very large problem with stochastic uncertainties into the parameters that you are considering them. And then a lot of problems come from this interaction. So complexity acts as an uncertainty amplifier in some sense. So we have a lot of available techniques to deal with complex and uncertain systems. Many of them comes from stochastic mechanics. So we have perturbation methods, stochastic finite element, polynomial chaos, statistical linearization, averaging techniques. So the whole set of methods that are developed in the frame of statistical mechanics and comes from statistical mechanics. Another approach is Monte Carlo simulation. So say that I do know nothing about my system, or more or less, so I know what is the general equation of motion, then I systematically modify the parameters, and then I build up a statistics of the response, and then I can elaborate these statistics in order to obtain statistically significant results. Then statistical energy analysis is a sort of analysis that is used in mechanical engineering to transpose the results that comes from statistical mechanics to engineering mechanical system. And the one that we are proposing, so a Hamiltonian damped system, is an approach that can be used purposely to solve this kind of problem. There is another aspect that is important, because damping in engineering could be a design key, and in other words, damping is widely used as a beneficial element in engineering. So everybody knows, for example, that I can use damping in order to avoid very big problems when I have resonances into my system. So it is something that can help the system to have a better response. Of course, on the contrary, in some cases, engineers contrast damping for better efficiency of device. But this point is very important, as I will show you. New understanding of damping as a tool for routing energy, so in the point of view that we are using. So damping is not dissipation of energy, but just is moving energy from one part to another part of the same system. So is an energy routing, actually, can form the basis for new technology for reduction of structural vibrations. And I will show you some example in this sense. Just a final remarks about the context of the present investigation in physics. You know that quantum mechanics is a generalization of Newtonian mechanics based on Hamilton formulation. So actually, if you can able to write for your system the Hamilton equation, well, I can have a classical problem in mechanics. I can study if the Hamiltonian is available, and so if a Hamiltonian formulation for this problem is available, I am able to produce a quantum mechanical model of the classical model. So an important problem is the understanding of quantum mechanics for dissipative system, because the presence of dissipation in classical system creates a very thorny problem for introducing generalization in terms of quantum mechanics, because if system exhibits dissipation, actually it cannot be treated as a Hamiltonian system, and it leads to some problems in generating a quantum mechanical model of our system. So elements of a Hamiltonian damped system can support this point of view in generalizing or in trying to produce quantum mechanical models for dissipative classical mechanics. So tomorrow I will start with you with the analysis of the V function and Q function in order to produce a sort of mathematical frame for this analysis. So if you have questions.
So maybe we can start discussion. I want to tell you a story which may be of interest in the context of what has been said. Damping and dissipation are two words which are used in a sense which is very similar. So actually, when you hear about damped Hamiltonian system, you can jump on your seat. This is due to the fact that nominalistic approach to science must be used, and you must be very careful when you use words. In this, mathematicians are very good because they teach us how to be precise. The story I want to tell you, because it's late, we say something not too much complicated, concerns the word flowing concerning rivers used in ancient Egyptian. In ancient Egyptian, flowing means going is invented combining different words. Going towards north. And the reason is clear. In Egypt, the river is flowing. Okay? Then a famous explorer went in Mesopotamia. And he wrote a letter back to his friends. He said, here, water is flowing towards north, towards south. Which is rather a contradiction. The problem when choosing words and symbols in mathematics or in science is this one. So, the organizing committee of CHISM obliged us to introduce an engineer in our group. And Professor Carcaterra was introduced. But you have seen, he can even talk about quantum mechanics. So for being an engineer, it's rather complicated. However, if I were Professor Carcaterra, I would start with a very formal definition of dissipation and damping in order to make clear that in his language these two words are completely different. But I mean, this is not...
Well, it is included, just because of my education. It's just included into one of the slides, in which, of course, the system is conservative, comes directly from the fact that the system is Hamiltonian. So you have a function that is time invariant, that is total energy. That is the first point. So what is a conservative system and what is the frame in which we are considering our system is very clear. So if the system is damped, means that observing a particular special degree of freedom of the system, you can see a progressive reduction of the amplitude, meaning that you have a trend of the amplitude that is decreasing, and as we see tomorrow, we can ask, in order to realize a sort of pseudo-damping, we can impose a condition of asymptotic vanishing of the response at a single point, that is the point that is actually observed.
We will check your mathematics.
Oh yeah, okay.
Talking about the lecture of Sergei, I will tell you that I appreciated very much the fact that he started specifying which were his kinematical descriptors, and then he started making calculation. This is the, how to say, orthodox behavior of this church, in a sense. But it is very old practice. I would say this is very interesting. Finally, I tell you an important, I tell you now the first time, Sergei, you should switch with Gilles your hour of lecture. So, because Gilles has, Professor Frankfurt has to leave Friday. So you will anticipate his lecture, and Professor Travillo will talk on Friday. Concerning what Professor Frankfurt is telling us, I will try, I don't know if I will be able, to show you that our kinematics in porous media, but in general, discontinuous continuum bodies, may be of use, I hope, in this research, because we have boundaries which are moving and at which you have discontinuity. and sometimes discontinuity of displacements. However, as the School of Global Physics is teaching me, when you have discontinuities of displacement, you have a material surface. So you cannot have bodies which are entering in others, or we don't have the kinematics of opening of cracks. So we have what Sergei told me is called a contact surface, right? You got it. Yeah?
My definitions classical.
Yeah. So we should try to discuss about these topics, because if you want to find more general models, you need to find immediately more general kinematics.
So, you formulated your imposed displacement above. My first question, if you impose some stresses, because this is also a physical statement. So,
here is a problem is, so I don't want to talk about special force.
but if you don't want to do that,
I didn't want to talk about Gibbs, but you forced me, so whatever. No. You know, of course, there's always trouble. So okay. So let's say you're applying forces here, like what? That's what you said. So you're doing what's called a self-implied standard experiment. Let's say I have a cube, I pull on it. Here is a little problem that you're having with all the following. You know, before you scoff at it, think about it a little, and then before you say, "Oh, that's ridiculous," think about it. So here's the thing. So I'm applying here a force, TG. So G is a force, or maybe I should call it F. It's a force per. I know a bit of mechanics. So it's a force per unit of surface. Yeah, that's right. So let's say it's constant. And let's say I want to minimize integral of omega let's say grad u squared. Let's do some grad u squared plus K times the length of gamma, I call H1 gamma.
You mean integral over delta or integral over?
Well, that's my integral. Over U gamma. Subject to the fact that grad UN is equal to Pn on that part of the Q x. The Q low, the bottom. And then 0 elsewhere. We put 0 as forces. Grad UN equals 0 on Q omega minus Q omega. Well, here's the problem with global minimality. Actually, it's a problem with minimality. Here's what I'm going to do. Gamma.
Just a second. This problem is a bad one because your functional doesn't fit the values of normal derivative on the boundary. You may change the normal derivative on the boundary. Usually forces are included as a linear function, right? But if you cannot prescribe...
Sorry, minus integral, sorry, of course, I must be telling you, yeah, you are absolutely right, sorry. So what is it? Yes, so that's nothing, of course. So it's a minus integral over d omega b of t f u.
Okay, we meant it in the weak sense.
No, I made a mistake.
Most strong
No. I made a mistake. So of course, forces are not part of your kinematic.
Yes.
The lesson 1 in Francesco's lectures. But anyway, so you do this and you want to minimize. Clearly, here is what you do. As soon as t is different from 0, you cut. How much do you pay here? You pay k times, say this is the square of side a, pay ka. Here, how much do you pay? Well, you pay if you take gamma to be as close as you want, the gamma to the surface, you pay 0. And here, what do you, for example, take u to be anything you want, to be a constant displacement, which is in the direction of your force. So you take u equals some constant times f with the right dimension, so that u is a displacement. So and constant which is positive. Then what you get here, you get t f squared times the length, so ta f squared. So it's not as ka minus ta squared. So now instead of c, there's a c. Where is c? Here. So what is the minimum of this thing? I have the right to any u that I want. So I take c to go to plus infinity, and I get that this is a minus infinity. So global minimality plus cracks is impossible because, this formulation, because immediately you're driving your problem of minimization to minus infinity. That's my answer. So that's why I cheated from the start. I put only displacement boundary condition. Now, you can create a class of forces for which we can do this global minimization.
But just a second. Your set of cracks is what you describe. This is the thing which you put in formulation. So you can avoid such a situation, just avoiding the situation when the crack cuts the material into parts. Just say you allow only the cracks which go from one side to the half of the specimen. This is your kinematic constraint. So that in this case the problem is well posed, is it? Right.
No, first of all, okay, no. The problem would not be well posed because I could create cracks. I could create a sequence of cracks that would be like that, that would converge to a crack which is like this. I could make it smaller or cracks.
But did I get correct your statement of the problem that when you allow cracks only from a certain set which you prescribe, denoted by gamma. So and the gamma of t was part of gamma, and gamma is, as I assumed, is a prescribed set. Is this right?
It's a set of all objects, all curves which are rectifiable with finite length.
Oh, so this is not a constraint.
No, it's not.
Oh, all right.
And there's no constraint that you can put into this problem that will be stable. That is, that will be stable under this kind of minimization process that we avoid this. No, it's a huge, this is a huge obstacle to considering forces. I don't want to discuss more about this. Global minimality does not agree with forces. Okay. If you want to do forces, you cannot do what I'm doing. By the way, depending on you guys, I may decide to switch. I don't know, maybe I should. But if it is more interesting, I don't know, maybe I should, but I'll ask you. I can also talk to you, instead of going into the numerical, later on I wanted to go to the numerical approximations of what I'm doing. But I could switch and talk to you more generally about rate-independent dissipative processes and how they are all modeled the same way within this kind of formulation. So that this is not specific to fracture. We can do elastoplasticity, damage, and other things like that. So it's maybe I'll need some feedback so that I can maybe decide. Tomorrow I'll keep on talking about fracture, but then I can switch if that's, depending on whether your interest is more in the topic of fracture or in the more general principles of how to write evolution problems that would have some dissipation in them and damping on the damping, but dissipation for sure. By the way, you can have problems that have dissipation and no damping as well. Not only damping, but also damping and no dissipation.
Since I'm interested to see the difference of your model and from one damage model.
Okay, so that is precisely the issue. If I'm not to discuss this with respect to damage, then I probably I need to keep on doing what I originally planned to do. So, okay, you're interested in that, I'll have to get the feedback of the people. If they're interested really in understanding how this is, what is the connection between this and damage, then I keep on doing that. Okay. Okay. Other questions? Two other speakers.
So maybe we stop here.